All right, hello everyone. Let's get straight to it. Today, the topic is electrochemical cells. Okay, so what is an electrochemical cell, or galvanic cell, or voltaic cell? All right, let's talk about it real quick. When you see the word electrochemical, that means that we are producing electricity from a chemical reaction. All right, do not confuse this, please do not confuse this with an electrolytic cell. I will be making a video of this very soon, but these two are not the same thing. Okay, so when you see electrochemical, I want you to recognize this is also known as galvanic or voltaic because it produces volts, produces electricity. So let's talk about how this electricity is produced and how to classify what we see here in this contraption. All right, so we have this nice balanced reaction that helps explain to us what exactly we're looking at, right? And it looks like we have two Ag plus ions plus one copper solid atom forming a copper 2 plus ion and two silver solid atoms. All right, so what's the importance of looking at this? Well, if we want to break this down into half reactions, which is usually a good idea to do, and because this is what's known as a redox reaction, we'll break it into its respective reduction and oxidation half reactions, which when combined will give us our balanced equation. So, first things first, what's being reduced, right? And remember, reduction is the gain of electrons, okay? That's what this is. This is the loss of electrons. There are some mnemonics like oil rig and Leo-Gur, which you may be familiar with. But even in that scenario, what we have is the gain of electrons in reduction and the loss of electrons in oxidation. All right, so how do I figure out what's being reduced? Mainly, the thing that is gaining electrons is usually the thing that's already an ion. And this is when you have positively charged ions, of course, but in this scenario, we have two Ag plus ions, which obviously have a positive charge. And since each one has a charge of positive 1, I know that it must gain two electrons to form two Ag solid atoms. Okay? That is clear to me from this part of the equation. Boom, turns into boom. If it's going to go from an ion that's positively charged to a solid, which is typically neutral, that means that it goes from positive to 0, which means there was a gain of electrons, which we said is reduction. Okay, let's look at the oxidation half reaction. That would be the copper going from solid form to being oxidized into copper 2 plus, which happens to be the charge of copper in this case. That could change, you never know. And then in this scenario, we have two electrons being oxidized. And the reason why copper might have different charges is because it's a transition metal, but in this scenario, we're not worried about that. Same thing with silver. They're telling us what the charges are, so no need to worry. Okay, and we have two electrons on both sides of this, right? So two electrons are being gained by the silver ions, two electrons are being lost by the copper solid atom. Okay, amazing. So now that we know this, let's talk about classifying the different electrodes that exist here. There's two of them, right? So an easy way to remember this is a mnemonic known as anox, if I can just write here, and red cat. So when you see this, you can picture an ox and a red cat, whatever helps you if you need some visualization. And what it means is that the anode is where oxidation takes place, and the cathode is where reduction takes place. Simple as that. So, in this scenario, copper is being oxidized, as we wrote in our half reaction, so you can see that it is a copper anode. And it happens to have a negative charge, or at least that terminal does. So what's the reason for that? If you think about what's happening, it's losing electrons. Where do the electrons go? Into the cable, right? Step 2, electron flow from anode to cathode. Electrons are negatively charged, right? So because this is the source of our negative charge, that is negative. Where does it go? To the positive charge. You've probably seen this on a bunch of different batteries where it's negative and positive, and if you put it the wrong way, it doesn't work. Well, there's a reason for that. So in this scenario, we want it to go from negative to positive. Okay, So that means that the silver cathode electrode is the cathode, right? And that means that it's going to be reduced. So if you can tell from here, these arrows actually tell us which one's going to get bigger and which one will get smaller. So it's no surprise that the copper anode will corrode because it's being oxidized. It will get smaller physically. The copper solid size will decrease because these copper ions will be going into the solution. All right, we'll talk about those in a second. Conversely, the size of our silver electrode, the cathode, will increase, right? And this is because our silver ions are gaining electrons. So they're being reduced and they're turning into a solid. When the size of the anode is very small or pretty much negligible, then at that point, your battery is basically dead. You need to either create more of this anode, get more of it. I don't know. You got to find it somewhere, recreate it, flip the reaction as if in an electrolytic cell, which will actually reverse everything, but we'll talk about that in another video, or you go and get a new battery. Okay, so now that we've gone through all that, let's talk about the salt bridge and the relationship that it has with the solutions. So typically when you look at electrochemical cell, you'll see it as two different solutions, which is very, very typical. And what you see is a salt bridge that connects them. Okay, what's the purpose of the salt bridge? The salt bridge is to help form a connection between these solutions so that there's an equilibrium of ion charges. You want the ions to balance out. What does that mean? Okay, so the copper ions that are formed here, right, make this part of the copper nitrate solution, and nitrate is just a negatively charged, soluble with everything, polyatomic ion. So that's the purpose. So you don't have any insolubility issues, if you were wondering. And the salt bridge is going to cause nitrate ions that's found in the salt bridge, sodium nitrate. The nitrate ions will go this way because we had an increase in positively charged copper ions, right? So they came from the solid, they became positively charged because they're oxidized, they lost their electrons, and now the negatively charged nitrate will move in this direction to help balance out that positive charge increase. Okay? And in the other solution, our sodium ions will move towards, guess what? The nitrate ions that are found in our silver nitrate solution. The reason the solution will be more negative than it will be positive until the sodium ions come through is because we're losing silver ions, well, not really losing them, but we're turning them into solid, right? So it's no longer going to be aqueous, it's going to turn into the increase of size of the cathode that we talked about earlier. Okay, so this is an overall explanation of how galvanic cells work. In this case, we looked at silver and copper. It could be different. There is a reactivity series that you can look at that will help you determine what is more likely to be reduced or oxidized. There are also reduction potentials, which are experimentally determined, which help you figure that out. You can also use those reduction potentials to find the E cell, okay? And that can also be used to determine delta G of that cell, which will help determine spontaneity. I will make another video about this that talks about this in detail. I will also make another video about electrolytic cells. And thank you so much for watching.